Good morning, sir.
Yeah, very good morning. So we'll pick things up from where we stopped in our last class. We already started our discussion on interpolation techniques. And so far, we were able to look up polynomial interpolation, looked up the spline approximation techniques and the Hermite interpolation. And then we're able to consider some approximation techniques where we have to trace the entire points in the relative to the distribution or the functional call. So now we are going to be looking at some other techniques that could be used for the approximation of functions, beyond what we already covered. And now we'll be looking at techniques like the least square approximation techniques, where we now have to figure out a function that may not necessarily trace the entire points or connect the entire points, but would rather minimize the error between the actual and the approximated function. Then we'll also consider some other, polynomial approximation techniques, the likes of Taylor series and Chebyshev polynomial. And then we'll also, if we have enough time, we'll also consider Fourier approximation, which you're already used to, which is a technique that represents the periodic functions using trigonometric series. Okay, now at some point we get to see that the least square approximation technique could cover the range of discrete functions and continuous functions. So we're going to also look up these techniques, where we now begin to look up some of the techniques that could be used where we have the data points specified, which we could literally say are discrete data points. And then we'll also consider some of the approximation techniques that could be applied if we have a continuous function. And this is where the Fourier approximation technique comes in, which you're already used to. We also have techniques like the Legendre, that is Legendre. Then we also have the Laguerre, that's technique. And there are some tests that literally places the Chebyshev technique here, but we want to try as much as we can to separate the Chebyshev technique from the least square technique. Although, in terms of approximating the error, we will still come to that, where we now have to talk about the Chebyshev norm in terms of approximating the error in the function, when we now have to compare the function itself and the actual and the approximated, and then how do we minimize the largest absolute error? So that will bring us to the maximum norm. Okay, so we'll come to all that. Okay, but just for us to begin, looking up the foundation we already established coming from interpolation techniques. So we'll just follow suit by talking about polynomial approximation. So in this case, a function is literally represented using polynomial. And we already know what polynomials are. The variable is raised to some power. Okay, so one thing I would love you to take note of here is that this technique may not necessarily specify how the coefficients of the polynomial are chosen. And the methods that we're going to be looking at here are the Taylor series approximation and also Chebyshev. So we're going to take this one at a time. So start with the Taylor series polynomial approximation. So when we talk about the Taylor series, we want to express this function as an infinite sum of terms based on their derivatives, okay? And this is usually done at a specific point. So let's assume we want to express a function f of x at a specific point x equal to being the same as a. So the Taylor series expansion will be the same as f of s and the same as f of a at that defined point, plus the first time derivative of the function at that point, x minus a, plus the second time derivative of that function at that point, over 2 factorial s minus a squared, plus the third derivative of that function at that point, over 3 factorial s minus a cubed all the way. So one thing I wanted to note is that in this case, we are literally computing an infinite number of terms, okay? So these terms literally extend to infinity. And in practical systems, we'll say that this is quite impractical for us to have a function that runs to infinity. So for us to be able to come up with a practical system, we now have to figure out the truncation of this series. So at some point, we want to truncate this series, you know, after about n terms, okay? So we want to specify that term, and this is done by ignoring the higher order terms. I want to know that the more the terms, the better the approximation, okay? So if we want to do that, so it means I want to truncate this at some term n, then the approximation of this function will now become same as a plus the first time derivative of that function s minus a plus the second time derivative of that 2 factorial s minus a squared plus all the way to some n derivative of the function at that point for n factorial x minus a to the point. So we now refer to this truncated Taylor series as the nth degree Taylor polynomial. Okay, so we can literally compress this in the form n of x sigma, we're taking our values from 0 to n. That's f to the kth derivative of a over k factorial s minus a to the k. So this is now referred to as the nth degree Taylor polynomial. So you could literally refer to this as the truncated Taylor series. So we know that if we desire a function that is smooth and differentiable, then Taylor series should be the option. So it means that we want a particular function to be differentiable at a particular point, say an x being the same as a. Okay, so the drawback is that it is literally accurate only near that point. Okay, so the accuracy is only within this, point, and so it requires a function to be differentiable up to n times. So these are some challenges or drawbacks when it comes to applying the Taylor series approximation. So it should be noted that, like I mentioned earlier, that when we have a truncated term, the more the terms in the truncated series, the better the approximation, okay? And then the error introduced by the truncation is given by the Lagrange remainder term, okay? Which is described as rho sub n of x in the same of f of n plus 1, where this theta is the function, that's f of the function n plus 1 factorial s minus a n plus 1 for all values of the theta, being taken on values from a to x. And this we call the Lagrange remainder. Okay, so this Lagrange remainder term literally estimates the accuracy of the approximation. So let us look up a simple example. So let's assume we want to approximate a function f of x being the same as epsilon x at some point s being the same as 0.5. So here we want to truncate this series at the top 10. So we want to use the third degree Taylor series around x being the same as 0. Okay. So, but we want to find the approximation of this function at this point, but we want to truncate the series around x being the same as 0. So in this case, we can literally put up the expanded form of the series. So now we have p of 3 of x, since we are truncating at the top 10 of the series, of the Taylor series, will be the same as f of a plus f prime of a, s minus a, plus second time derivative over 2 factorial, s minus a squared, plus third derivative of the function over 3 factorial, s minus a cubed. Now, since the truncated third degree Taylor series is around x being the same as 0, so it means that s is the same as a is the same as 0. Then this truncated Taylor series will now be rewritten as p of 3x be the same as f of naught, f of 0, plus first derivative function of the x minus a. Now a is 0, so we can just substitute that in, plus the second derivative of 0, the function s minus 0 squared, plus the third derivative 0 factorial s minus 0. So this is going to give us f of 0 plus the first derivative function 0, then that's x, plus second derivative over 2 factorial x squared, third derivative So now we can now literally resolve the derivative functions. So we already know f of x is the same as epsilon naught. So if that is correct, so this is what we have. This is the function. So once we substitute x to be the same as 0, so our first function, keep this column, f of naught will be the same as epsilon 0, which will be the same as 1. Now the first derivative of this will be d dx, dx for x being the same as 0. So this will also give us epsilon of x for x equal to 0, which is epsilon 0, which is 1. And the same applies for the second derivative, which is the squared epsilon s dx squared, which would be the same as e to the s for s equal to 0, which is e naught equal to 1. And then this also applies to the third derivative, which will be the cube x dx cube, which will also be the same as ex for x taking on value being the same as 0. So it means that the function is 1, the first derivative is equally 1, and the second derivative is 1, and the third derivative is 1 at x being the same as 0, because the truncation is around x being the same as 0. So once we substitute 1 into this expression, so we're going to have the function to be the same as 1 plus x squared plus x cubed. So it means that the truncated series we now reduce to P3 of x will be the same as 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And we already know that this is 1 plus x squared, 2 factorial is 2 times 1, plus x cubed, 3 factorial is 3 times 2 times 1. So this will give us 1 plus x squared over 2 plus x cubed over 6. Okay. So this is the Taylor series approximation for a given function. And now we are also expected to approximate the function at x in the same as 0.5. So that P3 0.5 will now be 1 plus 0.5 plus 0.5 squared over 2 plus 0.5 cubed over 6. So this will give us 1 plus 0.5 plus, this will become 0.125 plus 0.0208. So we're going to have 3, 0.5 to be the same as 1.64. Okay. And if that's what we have, now we have P 6, 4, 5, 8. Now we know that the function is the same as f of x being the same as epsilon x. And from this, we can literally calculate the actual value, okay, at x being the same as 0.5 from the function. And this would be the same as epsilon 0.5, which is the same as 1.6487. So that the error in this approximation technique will be the actual value, which is 1.6487 minus the approximation or approximated value, which is 1.6458. And this was going to be approximately 0.0029. Yeah. Okay, so this is the true error. Okay, and can say that the error is relatively small, and as such, the Taylor's approximation technique is literally or relatively highly accurate. Okay. Now, that's about it for the Taylor series approximation. Now we can look up the Chebyshev polynomial approximation. So before I move on, do we have any question on this?
No question, sir.
Okay.
I have a question, please.
Okay, go ahead, please.
Yeah, please, could you please go through this last page again? The P305, I know we got 1.6458. This second value, so I'm not sure where we got the value.
Okay, this value,
Yeah.
this is the absolute value. So we are literally substituting this into the actual function at this point, not from the approximation. So we got this from the approximation, the Taylor series, okay? So yeah, you know, we already saw that P of 3 of x is the same as 1 plus x squared over 2 plus x cubed over 6. Now, this is what we got based on the truncated Taylor series approximation. And so in substituting 0.5 into this approximated series, then we're able to get this. But we now want to look up the error in this approximation technique. So what we now did was to substitute that value into the original function which we approximated using the Taylor series. And that gives us this. I don't know if that's clear.
Okay, it's clear now.
So by taking the yeah, go ahead.
At what point do we say do we assume, because now we have 0.0029 and you say it's a true error. So
yeah,
at what point is there a limit to the true error we can have?
Okay.
Or it could be any value.
Okay, perfect. That's a good question. So how do we estimate the true error in an approximation, in the approximation of function? So we are literally taking the actual value minus the approximated value to be able to estimate the actual true error in that system. Now, we could also, in this analysis, estimate the error using the Lagrange remainder term, okay, to check for the error in the truncated series itself. You're going to see it's going to be different from this, okay? It will be different from this because then you'll be evoking the formula of 3 to the x, which will be the same as the function relative to zeta, s to the 4, in this case, over 4 factorial, okay? And now zeta is taking on values from 0 to 0.5. That is the limit, right? That is the limit from 0 to 0.5. So once we plug that into the process, so it means that this function now, which is n plus 1, that will be to the 4. So it's going to take on the highest value such that f of 4 zeta will be the same as the value of the function at that value, okay? So then once we plug in 0.5, so this is literally at 0.5, which will give us, we already calculated at 1.6487, right? So we can now plug in this into this. We know what x is 0.5. And now this is 4 factorial. So it means that, let's change the color. So what is already getting messed up. So the Lagrange remainder, term here for the 3 terms will now be the same as for 0.5. So let's just plug that in. For 0.5 will now be this value, which is 1.6487 over 4 factorial. So this will be 4 times 3 times 2 times 1. Okay, so that's going to give us 12 times 2. That will give us like 24, right? Times x to the power 4. So this is going to reduce to 0.5 to the power 4. And 0.5 to the power 4 is what? That will be 0.5 times 0.5 in 4 places. That will be 0.0625. So now we see that the error in the truncated series, which is given by the Lagrange remainder theorem, is not going to be the same as the true error in this series, because this is giving us the error due to the truncation. So as we increase the number of terms in the series, this truncation error will also reduce, right? Now it will also reduce, because then the divisor will be, we literally increase, right? Will increase, while this numerator will remain the same if we are still considering at the same point. So this will remain, but this may not remain, right? So this will not be a function of the number of terms, right? Going by the formula. So that will be x minus a n plus 1. So this will also increase, while the denominator will also increase. But at some point, we'll see that the error will reduce. We could play with this. And now, what are we going to get here? 1.6487 divided by 24 will be the same as 0.0043. Okay?
0.0043.
Yeah, so this is a little larger than the true error, right? So based on the truncation. And we know that by the time we increase the number of terms in the Taylor series, we are going to have a better approximation because the error will drop, okay? So this error is a little high because of the number of terms we have in the series. So how do we know the best error threshold? The closer to 0 the error is, the better the approximation. Does that answer the question, please?
Yes, it does. Thank you.
Sorry, I didn't get that thing you said, sir.
Yeah?
You said the closer the
error is to 0. So because we are literally looking at the best approximation of the function. So we want to approximate the function with some degree of accuracy. So it means that the difference between the actual and the approximated value should be minimal. Okay, so when we get to norms, you will see how we try to figure out that error threshold. We'll begin to talk about your absolute norm, your Euclidean norm, your super norm, which is your maximum norm, or Sobolev norms, and all of that. Because those are techniques used to estimate the error threshold. We want to minimize the approximation error to the barest minimum, so as to get an approximation of the function that literally models the system with some degree of accuracy, high degree of accuracy. Does that make sense?
yes, sir.
Okay, so I think we can move on. So now we want to look up Chebyshev polynomial approximation. Now, the Chebyshev, one thing I would love you to take note of here is that the Chebyshev polynomial approximates a function over the interval of -1 and 1. And someone may want to ask, why? So what happens if we try to approximate a function outside this interval? Okay, so what we're trying to say here is that the Chebyshev polynomial literally minimizes, yes, it minimizes the maximum error. So this is to minimize the maximum error. And that's why we usually refer to this as the maximum norm. Okay, so when we get to talking about norms, where we talk about the what's it, absolute norm, Euclidean norm, and then we're also going to talk about the maximum, the maximum norm. Okay, so talk about that as well. So when we get to that, you will now realize that we literally refer to the maximum norm as the Chebyshev norm. Okay, so where we use infinity to refer to the maximum norm, so that given a function, the maximum norm of that function will be written as this, which is the supremum, of the absolute value of that function. And then this is usually integrated over a range of points. Okay. But the idea about the Chebyshev polynomial is to minimize the maximum error, and that is what the maximum norm does. Okay. We want to figure out now. You should take note that this does not take care of the entire error. So if we want to take care of the total error, then this does not solve that problem. Okay, because this literally targets the worst case error. Okay, so if, for instance, you are concerned about minimizing the maximum error over a given interval, then the Chebyshev polynomial approximation of function becomes your choice. Okay, and the reason we literally integrate or take this approximation of function over this interval is that it is more stable within this interval. Okay, so the Chebyshev, let me just put that down. Now, Chebyshev polynomial, naturally defined, and are also orthogonal over the interval -1 to 1 because of one, their mathematical property, and also the weight functions. So in considering this polynomial approximation, it is observed that this Chebyshev polynomial approximation is well behaved and stable within this interval. Okay, and if you have to now apply this technique outside this interval to ensure stability, then you have to enforce a transformation of the interval. Okay, now for us to be able to therefore apply the Chebyshev polynomial approximation technique, we have to literally force, or better say, restrict this polynomial within these intervals. Okay? And then we can now provide a formal description of the polynomial, because the Chebyshev polynomial are generated using the recurrence relation. That is, polynomial Tn plus 1 of x is the same as 2x Tn of x minus Tn minus 1 of x. Okay? So with this, we are able to develop the polynomials for different values of n. And also, we see that the Chebyshev polynomial could also be defined in terms of the trigonometric function, such as Tn of x is the same as cos, then n cos inverse of x for x taking on values from -1 to 1. So it means that this is so because the cos inverse of x is only real valued within this interval. So outside this interval, it's not revalued. So this naturally restricts the Chebyshev polynomial to this interval. Okay. And also, it should be noted that the Chebyshev polynomial satisfies the orthogonality, because we know for us to say that two functions are orthogonal, then it means that the inner product of those functions, say by I, by j, must be equal to 0. Okay, so it means that the Chebyshev polynomial also satisfies orthogonality in the sense that once we integrate this over the interval, then we can say that should we multiply a scalar by the polynomial, by the product of the polynomial, the x, this should be equal to 0, which is the inner product. And in this case, we see that this scalar is the same as 1 over square root of 1 minus x squared. So this is a weight, it's a weight function, okay? So this is the weight function. And the weight function is to enforce stability, right? So, and in this case, this weight function, beyond enforcing stability, it ensures orthogonality over this interval. So we don't want this to diverge from this point, okay? So for us to be able to maintain orthogonality between -1 and 1, then the weight function has to be 1 over the square root of 1 minus x squared, okay? So in other words, this weight function is not defined outside this range. So the weight function is only defined within the range of -1 and 1. So this is literally one of the reasons why the Chebyshev polynomial are primarily used within this interval, okay? And another thing I want to mention is that although the Chebyshev polynomials are defined within the interval of 1 minus 1, like I mentioned earlier, we could also adapt the Chebyshev polynomial to some other intervals beyond the 1 minus 1 by performing some kind of linear transformation. So that x will be the same as 2t minus a plus b over b minus a. So in this case, t is an element of a and b, okay? So this transformation literally allows the Chebyshev approximation to be used for functions defined on any finite interval, okay? Now, we now want to consider some other details. So how do we provide a formal definition or expression for the Chebyshev polynomial? So we now want to say that the Chebyshev polynomial, denoted as Tn of x, form a set of special orthogonal polynomials defined over the interval -1 and 1. And they are given by the recurrence relation, which I already gave the nth order formulation. So the recurrence relation, T0 of x is the same as 1. So T1 of x is the same as x Now, T2 of x is the same as 2x squared minus 1. T3 of x is the same as 4x cubed minus 3x. So we can literally go on and on by using the nth order formulation, which is the same as 2x Tn of x minus Tn minus 1 x for n greater or equal to 1. So we literally use this nth order formulation for n greater or equal to 1. So when n is 1 here, so we're going to be having T2. So this would be T2, and you see that for T2, so this would be 2x times T1 of x, and 2x, and T1 of x is x, so that will be 2x times x, that will be 2x squared, minus, so this will now be 1 minus 1, that will be T0, and T0 is 1. So with this formulation, we are able to develop the Chebyshev polynomials even to the nth order, okay? And I also mentioned that the Chebyshev polynomial in the trigonometric form is the same as Tn of x being the same as cos n cos inverse x. And this takes on values, x takes on values from -1 to 1. So what is important to us when we consider Chebyshev polynomial approximation is that they help in minimizing the maximum error when approximating functions. Okay, so that is the key feature here. So when we want to consider worst case error minimization, then we want to consider the Chebyshev approximation technique. Okay, so now if that is that, how do we describe the function? So a function, so we can now say that a function f of x, for instance, can be approximated using the Chebyshev polynomial as f of x being approximately the same as this sigma, for which k takes on values from 0 to n, c sub k of x. Okay, and here the coefficients c sub k are defined by 2 over n plus 1 sigma j taking on values from 0 to n f of x of j t sub k s sub j for all values of k taking on values from 0 to n. And here the Chebyshev nodes are given by s sub j being the same as cos 2j plus 1, where j is some integer value, okay? So it could be 1, it's not a complex quantity, okay? So j in this case could be some integer values. Then times pi over 2n plus 1. So it should be noted at this point that the nodes also help in reducing the wrongs phenomenon. Okay, you know, when we talked about interpolation, we said, well, we usually have a problem or a challenge with approximation or with our function when we use the regular interpolation techniques, such as having large oscillations at the edge of the intervals, okay? And we call such large oscillations as the Runge phenomenon. So one thing the Chebyshev approximation or polynomial approximation does is to deal with such worst case errors, okay? Because we do not need too many outliers in our approximation, okay? So you now see that the Chebyshev polynomial approximation technique helps reduce the Runge phenomenon, okay, for the observed polynomial interpolation. So I already mentioned some of the key properties before we look up an example, so I will just mention them again. So orthogonality is a key factor. And
so, sir, I have a question.
Go ahead, please.
So for the maximum error we have, is there a limit, or no? We just take it when we're considering a polynomial. So we just look at the polynomial and we look at the maximum error we have for that polynomial. So is there a limit as to maybe in a particular value for which a Chebyshev can be used to correct that error, like the root?
And that's the good thing about the approximation technique. And I'm sure the question you just asked will become even clearer. The solution to that will become clearer, how we determine this maximum error when we begin to talk about norms, you know, the maximum norm, okay? Where the supranorm, where we now have to deal with the worst case. So for the given approximation, we may not be able to tell at what point this error exists, okay, by mere inspection or observation, okay, except we run through the iteration. But what this technique does is to average the value. And we're going to see how that averaging is done when we talk about norms. Okay, or better still, the Chebyshev norm. Is that okay?
Yes, sir. Thank you.
Or is it that are there still some doubts? Probably I didn't clarify properly, so that I clarify.
No, like you said, when we start looking at the norms, I think there will be more clarity to it.
Okay, because
Doctor.
Okay then.
Hello, sir.
Yeah, go ahead, please.
Yes, sir. So sorry, I put up my hand before. You didn't see it.
Oh, sorry for that.
Yes, sir. I want to ask a question. How do you arrive at the T naught of X, T1 of X? Or is it?
Yeah, that's why I was
then T2.
They are derived through the recurrence relationship. Okay, so they are derived.
Okay.
Yeah. So
okay.
It's when we also talk about the Legendre and Laguerre's approximation techniques, we see that we can also use the recurrence relation, but there is also another technique, which is the Rodriguez relation. Okay, so these are great guys who went on to figure out an approximation to figuring out these polynomials, okay? And they are derived. So you could look up some standard text to see how they derive the first Chebyshev polynomial to be a constant, okay?
Okay, thanks, sir.
Yeah, so for now, we just take them to be statutory, but they are literally derived using the recurrence.
All right, sir. All right, sir. Thanks, sir.
You're welcome. So now some of the properties I already mentioned, we mentioned orthogonality, and we said, well, this is one interesting property that makes us, perform our operation within the defined limit. So Chebyshev polynomial literally satisfies the orthogonality condition, such that the inner product between two polynomials is the same as taking the integral within the limit rho of s Tm of x dx should be equal to 0. So once the inner product is 0, then we know that the functions are orthogonal for all m not being the same as n. Okay, and here we know that the weight function rho of x is actually a scalar product, and this weight function
The integral from -1 to -1, or you're going to write -1 to 4.
Oh yeah, yeah. Sorry for that. So I was literally writing what I was not thinking. I was not writing what I was thinking. Thank you for that observation. And then we already explained that this weight function is the same as 1 over the square root of 1 minus x squared. And this takes on real values between the range -1 to 1, right? So that is one of the properties of the Chebyshev polynomial. And then we have some other properties. We already know that it minimizes the maximum error in the approximation or in the function. So the Chebyshev approximation provides a near optimal polynomial approximation in terms of minimizing the maximum deviation from the true function. Okay, and we should note that this minimization of the maximum deviation from the true function should not be confused with the minimization of the total error in that approximation technique. Okay, well, when we also begin to talk about norms, the ways to minimize the errors in a function, this will also become clearer. Okay, so we can equally estimate the extrema and the roots. Okay, so we know that the extrema of the Chebyshev polynomial occurs at s of k, given as cos k pi over n, when k takes on values from 0, 1, all the way to n. And then the roots of the Chebyshev polynomial are equally given by s of k being the same as cos 2k plus 1 pi over 2n for k for the 0, 1, all the way to n. Okay, well, these are just by the side, okay? Now, let us look at an example. Let's see how this is literally done to appreciate the Chebyshev polynomial approximation. So now, we want to approximate the function f of x being the same as e to the x. Using the Chebyshev polynomial, we want to use the Chebyshev polynomial up to degree n equal to 2, okay? So we already know that the Chebyshev polynomial, once we expand the formula we are given, who can recall the formula, the Chebyshev polynomial? Let's, oh, no. We mentioned that the function is approximately the same as k, taking on values from 0 to c sub k of x, right? Yeah. So for n being the same as 2, the polynomial to degree 2 of x will be the same as taking on values from 0 to 2, right? So that would mean we have c naught, t naught of x plus c1, t1 of x plus c2, t2 of x. So this is the Chebyshev polynomial that will minimize the maximum deviation in this function. And we already know that through the recurrence relation, the Chebyshev polynomials are already defined. So the Chebyshev polynomial T n of x for all values of n being the same as 2 is given by the recurrence relation as. So we already know T naught of x is the same as 1, and T1 of x is the same as x, and T2 of x is the same as 2x squared minus 1. And then this polynomial expression will reduce to something, say, C naught plus C1x plus C2 into bracket 2x squared minus 1. So the challenge now is figuring out the coefficients, right? So we need to estimate these coefficients. So how do we evaluate the coefficients? So once we are able to evaluate the coefficients, then we plug them into this polynomial expression. Then we are able to come up with the Chebyshev polynomial approximation up to the second degree. Does that make sense, please? Before I move on, does this make sense? Because all we need to do now is to figure out the nodes and then tell the coefficients. And once we are able to evaluate the coefficients, we plug the expression into what we have here, which is the same as this, and then we are good. Are we good for now? So before we move on to figure out, is it clear up to this point?
From now.
Hello, sir.
Yeah, go ahead, please.
Okay, so I just wanted to confirm. So if we are going further to this recurrence relation, assuming we are going to probably fourth order or fifth order. So the T3 is 3 sub 4, for instance, maybe the fourth order, the T sub 4x. How do we come up with the value?
Okay.
So how do we go about it?
So we are going to evoke the nth order formula. Let's let's change the color. That will be T n plus 1 of x would be the same as 2x T n of x minus T n minus 1 of x, right? So if we want to figure out, now this applies when n is greater or equal to 1, right? So it does not include at n equal to 0. So we already know at 0, it is the same as 1. So we already have for T2. So how do we evaluate for T3? So let's clean this line. So I'll just use a different color so as not to confuse things. So at n equal to 2, then this is going to be T3. At n equal to 2, so that will be T2 plus 1, that will be 3, T3 of x, right? So this will be the same as 2x T. Recall that n is 2 at this point. That will be T2 x minus T. 2 minus 1, that will be T1 of x. Now we already know T2, so that will be 2x into bracket 2x squared minus 1, right? That's T2, substitute T2 into this, minus T1, which is x. So this will give us 4x cubed, right? Minus 2x minus x. So this will be 4x cubed minus 2x minus x minus x, right? Are we in order? Hope that is correct. Yeah.
Minus 3x.
Is it minus? Okay, minus
3x.
3x. Yeah, minus 2, minus 3. Yeah, minus 3x. Perfect. So this is going to give us at T3 of x equal to this, right? So you set to the fourth. So T4 will now be the same as when n is 3. So for T4 of x, so that will be 2x T3 of x minus t. So recall that for us to have T4, n has to be 3. So 3 minus 1, that'll be T2 of x, right? So now we have 2x into bracket 4x cubed minus 3x minus T2 of x, that's minus 2x squared minus 1. So you want to resolve this again, then we get that. Does it make sense? Does this address?
Yeah, it does. It does. It does actually.
Yeah. So with this, we are able
Does it make sense?
Yeah. So with this, we are able to get the Chebyshev polynomial to whatsoever degree. So let's assume we say, okay, well, we want to do this up to the degree n being the same as 10. So you just derive all of those polynomials, then plug them into this. You have your long. So then it means you are literally aiming at a more accurate approximation. Okay, so that's why you want to go as far as that higher order. But just for ease of understanding, we are just keeping it simple, right? Yeah. So can we progress? Yes. Okay.
Yes, we can.
So the next point now is to figure out the coefficients, and we now recall that that the Chebyshev coefficients, the Chebyshev coefficients are given by the expression C sub k being the same as 2 over n plus 1. We have sigma j taking on values from 0 to n, f of x sub j, t sub k, s sub j. And this is for all values of k taking on values from 0, 1, all the way to n. And now for n being the same as 2, that's the degree we are going to. So it means that we can now figure out the coefficients. You know, now don't forget the coefficients we are literally interested in are C0, C1, and C2, right? So these are the coefficients. So, but we know that we got to this because n, where the degree of polynomial is the same as n it being the same as 2. This is the second order, okay? So we can substitute n into this expression so that the Chebyshev coefficient formulation will now reduce to C sub k being the same as 2 over 2 plus 1 when n is 2, sigma j being the same as 0 to n, f of s sub j, c sub k, s sub j. So this is going to be the same as 2 over 3, sigma j being the same as 0 to n, f of s sub j, c sub k, s sub j. Okay, and now we know that we have to evaluate for these coefficients, c sub k, for k, taking on values from 0, 1, 2, and then j also, we take on values from 0, 1, 2. Okay, so for C0, we already know that 2 over 3 into bracket f of S0, then we have T0, that's for k equal to 0, right? We want to figure out C0, right? So for C0, k is equal to 0. So all k remains 0. This is a little tricky. So I'd love you to just observe, right? And take this. K is not changing at this point, but j is changing. Okay, we are moving from the first term to the second term to the third term. Okay, so that J in this case, for K equal to 0, J moves from the first term, the second term, and the third term, right? So we now have f x naught, t naught, which is K, into bracket s naught, plus f of x1, which is the second term, t naught, K is still 0, s1, plus f of s2, which is the third term, t naught, s of 2. Okay. Does this make sense for now? So let us try for K equal to 1. So we now have C1 being the same as 2 over 3. So we now have f of s naught. Now T1 of s naught plus f of s1, T1 of s1 plus f of s2, T1 of s2. So at K equal to 2, we now have C2. We have C2 being the same as 3 over 2 into bracket f of first term s naught.
2 over 3.
2 over 3, sir.
Oh, yeah,
3.
2 over 3. Yeah, that's right. How we write what we are not thinking. Now I see why students fail when they are supposed to pass, right? So that's 2 over 3. Now, then C2 of S naught plus F of S1, T2 of S1 plus F of S2, T2 of S2. So with this, we've been able to develop the relationship to evaluate these functions. So we already have we have our function given, and then we have the polynomial, the Chebyshev polynomial. So now we want to figure out how to plug these things in. But how do we figure out S naught, X1, S2? We know that our T naught of X is a constant value. So how do we tell T naught of S sub I, where I now takes on value from 0, 1, 2. Let's assume it even goes to the 10th degree. So now we'll now have to develop the formulation for the Chebyshev nodes. Okay? Now you recall that we already provided the formulation for the Chebyshev nodes. That is how we'll be able to develop the relationship for these nodes, the X values, okay? So for us to be able to evaluate the coefficients, we now need to compute the Chebyshev nodes, and those Chebyshev nodes are S naught, X1, S2 in our case, for n being the same as 2. So it takes on values from 0 to 2. And the function related to these nodes. So once we are able to evaluate these Chebyshev nodes, then we now have to also figure out the functions that are relative to these nodes. And once we are able to tell these, then we plug them into the formulation for the coefficients, and there we go. So, but we know that the Chebyshev nodes are given by S of j being the same as cos 2j plus 1 over pi over 2 integral n plus 1. So, and we know that the value of j takes is from 0, 1, 2 for n being the same as 2. Okay. So from this, we know that n is the same as 2. So S of j will be the same as cos 2j plus 1 pi over 2 into bracket 2 plus 1. And this will give us cos 2j plus 1 pi. That'll be 2 times 3, right? This will be 2 times 3. So it means that S of j is going to give us cos 2j plus 1 pi over 6, right? Is this clear?
Yes, yes, sir, it is.
Okay. So I think now we can move on. So it means that S of j is the same as cos 2j plus 1 pi over 6. And we have j taking on values from 0, 1, 2, right? So for S naught, we now have cos 2, where j is 0, plus 1 pi. This will be over 6. So that will be cos 0 plus 1 times pi. That will be pi over 6. And we know that this is the same as square root of 3 over 2, right? Now, S1 will be the same as cos 2 times 1 plus 1 times pi, right, over 6. So this will also give us cos, that will be 2 plus 1, that will be 3 pi over 6. So this is the same as cos pi over 2, right? Yeah, 3 into 6, that's 2. And cos 90 degree is what? 0. Okay. Now, then S2 will be the same as cos 2 into bracket 2 plus 1 times pi over 6. So this will give us cos 2 times 2, 4 plus 1, 5. That will 5 pi over 6. So this will give us the negative of that. Yeah. So now we've been able to evaluate these values. So the next point is to estimate f of x. We know f of x is the same as epsilon x. Okay, so that f of S1 will be the same as epsilon S1, which will be epsilon. What's S? No, sorry, let's start with S naught, S naught, S naught. So what is S naught? Epsilon square root of 3 over 2. So once you resolve this, this is approximately 2.028. Now, f of S1 will be the same as epsilon S1, will be the same as epsilon 0.
How are you?
Is approximately
Too much energy.
and then f of S2 will be the same as epsilon S2. We already know what S2 is, epsilon minus square root of 3 over 2, which is approximately 0.493. Good. So now we've been able to evaluate these values. We know what they are, and now we can plug them into our expressions. We know what S0 is, we know what S1 is, we know what S2 is, we know what f of S0 is, we know what f of S1 is, and we know what f of S2 is. So let us resolve the coefficients. Now we know that C0 is the same as 2 over 3 into bracket f of S0, T0, S0 plus f of S1, T0, S1 plus f of S2 T naught S2, right? But we already know that T naught of X is the same as 1. So it means that T naught of S naught will be the same as T naught of S1, will be the same as T naught of S2, which will be the same as 1, because 1 is a constant. So no matter the point we take S1 from, it is a constant value. It's more like a DC value, right? Okay. And it's one thing we usually want to avoid in our electrical system. Okay, except it's desirable. Now, so we can now plug in these values. We already know what f of S naught is, which is 2.028. We know what f of S1 is, which is the same as 1. We know what f of S2 is, which is the same as 0.493 as derived. So it means that C naught will be the same as 2 over 3 into bracket 2.028 times 1 plus 1 times 1 plus 0.493 times 1, right? And this will be the same as 2 over 3, 2.028 plus 1 plus 0.493. So this is going to give us 2 over 3 times 3.521, which is 2.347. So C naught is the same as 2.347. So we can apply the same technique to evaluate the other coefficient, C1, which is same as 2 over 3, f of S naught, T1 S naught, plus f of S1, T1 S1, plus f of S2, T1 S2. Now we know T1 of X is the same as S, right? So that we can now evaluate this. We know what X is, right? For each of the points. So T1 of S naught will be the same thing as X. So what is X1? Will be the same as S naught rather. And that is square root of 3 over 2. Now, T1 of S1 will be the same as S1. And we already know what our S1 is, which is 0. And T1 of S2 will be the same as S2, because it's the same as X. So it means S of I, in this case, the same as S of I. And we know this is the same as negative square root of 3 over 2. And we already know what f of S naught is, which is 2.028. F of S1 is the same as 1. And f of S2 is the same as 0.493. So we can now plug in this. C1 will be the same as 2 over 3 into bracket 2.028 times square root of 3 over 2 plus 1 times 0 plus 0.493 times minus square root of 3 over 2. So once we resolve this, we are going to have 2 over 3 times 1.328, which is the same as 0.885 as C1. So C1 is the same as 0.885. Is this clear, please?
It is clear.
So now we can resolve the final coefficient, which is C2 in the same as 2 over 3, f of S naught, T2 S naught, plus f of X1, T2 of S1, plus f of S2, T2 of S2. But we already know that T2 of X sub I from our analysis is the same as 2S sub I squared minus 1. So it means that T2 of S naught will be the same as 2 into bracket square root of 3 over 2 squared minus 1. And then this is going to be square root of 9 divided by 4, which will be 3 over 4. That'll be 2 into bracket 3 over 4 minus 1. And this will cross this, and this is going to give us 1 over 2. And then T2 of S1 will be the same as 2S1 squared minus 1. And that will now give us 2 into bracket 0 squared minus 1, which is the same as minus 1. And then T2 of S2 will be the same as 2x sub 2 squared minus 1. And then that will give us 2 into bracket negative square root of 3 over 2 squared minus 1. And this brings us to the same value, which is the same as half. We already know what f of S0 is, which is 2.028. We know f of S1 is the same as 1. And then we know f of S2 is the same as 0.493. So once we plug everything in, that will be C2 being the same as 2 over 3. Then 2.028 times 1 over 2 plus 1 times minus 1 plus 0.493 times 1/2. So that's going to give us 0.173. Boom. I think we are there now. So we know all the values of the constants and the Chebyshev polynomials. So the approximate Chebyshev polynomial function will now be the same as P2 of x will now be the same as recall C0 of x plus C1 of s plus C2 of x. So we can now plug all of those activities in here. So we have 2.4, is it 4 or 3? No, 3. 2.347 times 1 plus C1 was 0.885, and T1 of x is the same as x. Then C2 was 0.173 times 2x squared minus 1. So we can now open this up. That'll be 2.347 plus 0.885x. So this times this, that will be plus 0.346x squared minus 0.173. So we can subtract this from this, and then we're going to have 2.174 plus 0.885x plus 0.346x squared. So the Chebyshev polynomial that approximates f of x being the same as e to the epsilon x is the same as this, okay? So it means that this Chebyshev polynomial is approximately the same as this function. And this is provided over the interval -1. This is to enforce orthogonality and stability, okay? So it means this polynomial is well behaved within this range. Okay. Now that we've done that, I think we can now move on to least squares approximation. So we just run through this.
Sir, excuse me.
Go ahead, please.
Hello? Okay. Yeah, is it possible to check the true error of the Chebyshev and compare it with the Taylor series that we did?
Absolutely. So you want to substitute that value into
0.5. Yes.
Yeah, so it means you want to take f of x equal to e sub x. So at 0.5. So at 0.5, then you also want to take P2 of x at 0.5, which would be 2.174 plus 0.885, 0.5, plus 0.346, 0.5 squared. So once you do that, then you can now take the difference between the absolute value and the approximated value. So this will give you the error in the approximation. I think that's fine, right? So you want to run a check. Is that okay?
Yes, it is okay.
So now you recall that when we considered the classical interpolation techniques, we literally forced the approximation curve to go through all the points. We talked about the quadratic spline, the cubic spline, and all of that. So we try, except for the Bezier spline, where we did not go through all the points exactly. But in the case of least squares approximation, we are not going to go through the points at all. You know, like as they say, at least not intentionally. So another point to note is that while we had a measure of the error of the approximation in interpolation, we did not, really have much issues with spline. But when we talk about the class of least squares method, we go even further and try to minimize the error of the approximation. Okay? So that's why we call it the least squares. Okay, so the least squares approximation is a method for minimizing the sum of squares of errors. Okay?
What is this TP or what is this? Is the method for
Minimizing.
Okay, so that's what it is. So now we want to get a perfect fit or a near perfect fit for our curve, as an approximation of the function. So this method is literally used for minimizing the sum of squares of the errors between the observed and the predicted values. So better still between the actual values, the measured data, and the predicted data. So we can also run through the classification of least squares approximation techniques. So we have, like I mentioned earlier, we have for the discrete functions, and we also have for continuous functions. So when we talk about the discrete functions, we want to talk about the linear least squares approximation. We also want to talk about the polynomial least squares approximation. Then we also want to talk about the least squares with basis function. Okay. Then for continuous functions, we want to talk about the Legendre. That's Legendre polynomial approximation. And the Laguerre polynomial approximation. Now also have the Fourier series approximation, right? Where we now have to disintegrate the sequence into the sum of sines and cosines, okay? So least squares approximations or approximation techniques for the discrete functions literally deals with discrete data points, okay? And the primary goal is actually to find an approximation function that minimizes the squared errors between the actual data points and the function values. So we'll just run through this as fast as we can. This is pretty straightforward. So let's look at the linear least squares approximation. So, well, this is literally the most common form of the least squares approximations, where the approximating function is a linear combination of parameters. So if we are given a set of data S of I, Y sub I, for instance, for which I takes some values from 1, 2, 3, all the way to n. So what we actually seek here is a linear function given as f of x being the same as a plus b of x. Okay? And here, the sum of squared residuals, or the error, is given as S being the same as sigma, taking on values from 1 to n, for which we have y sub I minus, that's the actual function, minus the approximate function, which is a plus bx, minus a plus b x sub I. Then it's a mean squared error, so we square this. So this is minimized. So this is what we want to minimize, right? Minimized. So for us to be able to evaluate AB, so what do? We literally take the partial derivative of x with respect to A and B, and then we set it to 0. So we want to check the S, the A, set this to 0. And also the S, the B, and set this to 0. So once we do this, we are going to come up with a system of equations that for which we will now solve the simultaneous equations and then get the values for A and B. And this is pretty straightforward. So if we differentiate this with respect to A, so what do we get? So that's going to give us -2 y sub I. So this will open this up, minus A minus B sub Si. 2 minus 1, that is 1. So that's what we get when we do this. And when we do this with respect to B, so it means that S sub I is also going to come out in this sum. So, and 2 is also going to come out. And then the function here is -b, so negative, so the negative sign will equally come out. So that would, now this will give us -2, this summation, then S sub I, since we are differentiating with respect to B, B sub I, no, X sub I is, it's not B, we are differentiating with respect to B, not with respect to S. So S sub I is now the coefficient in this case. So into bracket y sub I minus A minus bx sub I is equal to 0. We are equating this to 0. So now we have the system of equations. So by the time we evaluate the sum terms, term-wise, this will result in a system of 2 equations in 2 unknowns, A and B. So these equations are usually called the normal equations. And then that's the solution follows directly. So here, this will now lead to something you can still play with, NA plus B sigma SI sigma Y sub I. And then the other will reduce to AS sub I plus B sigma S sub I squared, which is what S sub I Y sub I. Okay. So by the time we solve this, and there we go. So in this case, let's assume we have some points. We just run through this 2, 3, 3, 5, 4, 7, for instance. Now, the first thing we want to do is to figure out these terms, right? These terms. So we can figure out S sub Si. So by the time we sum, this is S1, S2, S3, S4, right? This is Y1, Y2, Y3, Y4. So once we do that, that'll be 1 plus 2 plus 3 plus 4, right? 1 plus 2 plus 3 plus 4. So that's 10. So then the next thing is SI squared, right? Sigma SI squared. So we already have for this point and for this point. So that will be the same as 1 squared plus 2 squared plus 3 squared plus 4 squared. That will give us 30. So the next is y, sum of y's, sigma yi will be 2, 3, 5, 7, right? 2 plus 3 plus 5 plus 7. That will be 17. And then sigma SI, YI. So we'll multiply them, right? So XY. So that will be 1 times 2 plus 2 times 3 plus 3 times 5 plus 4 times 7. So that will give us 50. So what we now have to do is to plug all of these into this. And once we do that, we are now going to have 4A plus 10B equal to 17, and 10A plus 30B equal to 50. So we can solve the simultaneous equation. A is the same as 0.5, and B is the same as 1.5. Boom, we are there. We already know the linear least squares is given as A plus BX. So once we plug in those parameters, so what do we get? Y will be 0.5, 0.5 plus 1.5x. That's the least square approximation. So this is pretty straightforward, okay? And then we can evaluate the error and check whatever we want to do. So I'll just run through others for the polynomial least squares approximation. We are given the function to be the same as a0 plus a1x. So this is where we stopped for linear, but now that we're going higher order, so a2x squared plus all the way to amxm. And we are still dealing with the same thing. So we now have to check out for the residual, which we need to minimize, which is I taking all values from 1 to n. So here, y sub I is literally, we are subtracting this function from y sub I into bracket a0 plus a1 s sub I plus all the way plus am s sub I to the m, then all squared. So this is what we want to minimize. And once again, so we take the partial differential for all of these coefficients and equate to 0, and there we go. Okay, so we can literally perform the same thing. Let's assume we want to perform quadratic polynomial. So if we want to resolve an issue for, say, quadratic polynomial, so it means that this function is going to be the same as f of x, being the same as a0 plus a1x plus a2x squared. So this is where the quadratic polynomial stops. So we already know what this function is. And then the next thing to do is to expand the expression so that we now have sigma y sub I will be the same as n a0 plus a1 sigma s sub I plus a2 s sub I squared. It follows directly from what we did earlier. Sigma si yi will be the same as a0 sigma si plus a1 sigma si squared plus a2 sigma si cubed. Then sigma si squared yi will be the same as a0 sigma si squared plus a1 sigma si cubed plus a2 sigma si to the 4. So once you evaluate all of this relative to the given points, then you can now probably use either Gaussian elimination method or matrix method, because this is going to lead to a system of equations. Say here you now have, say, n sigma si all the way to sigma si to the m. Then we have sigma si squared all the way to sigma s sub I to the m h, for instance. Let's say then this goes all the way Then we have sigma S of I m, sigma S of I m plus 1. Then we also have sigma S of I 2m. So once we have this, this will multiply A0, A1 all the way to AM. So this will now be equal to sigma YI, sigma SI all the way to sigma SIM to YI, you know. And then we know that A times A is equal to B bar. So A bar will be the same as A inverse B bar. So you can now solve all of these. Then once you get the coefficients, then you substitute them into this expression, and there we go, right? Is that straightforward? And then another
Please,
yeah?
please, I have a question.
Go ahead, please.
No, the former slide, the former workspace. Yeah. So this summation xi square yi, we have a naught summation xi square plus a1 summation xi cube. I don't understand how that I becomes xi cube here for
Okay,
this
yeah.
expression.
Now you have to solve this. Okay, you know, you are literally differentiating
Okay.
s with respect to each coefficient. A0 equal to 0, then the s a1 equal to 0, then the s a1 equal to 0. So once you do this, so this is not linear, this is cubic, then you now come up with this. Yeah, just the same way we did with linear. So you can do this in your spare time.
Okay. Okay, that's clear. Okay.
So you are differentiating this and equating to 0 for all these three coefficients. And then you now arrive at the system of equations. Okay. Now let us.
Okay, that's clear.
Okay. Yeah.
From that question, okay, from here, sir, I think from any relation y high is equal to NAO. Is it NAO or MAO? Do you have any NAO?
Which one?
This one, the first one. Relation y high is equal to N.
A0, yeah.
So we don't have any N in the expression. That is equal to summation.
Okay. Now, well, when we are talking about the N, we are talking about the terms. We are going to N, like for the other, N is what? What did we evaluate as N? For the linear. For the linear.
Two.
Exactly. So as the order is going, then we'll be increasing the N values.
Okay.
Yeah. Okay, so I think we can move on now. Still have quite a few details to push. So we have the polynomial. This squares, yeah, this for polynomial approximation. For which of them haven't we looked up? Yeah, with basis functions. Yeah. So basis function. So let's look up least squares with basis function. So in this case, instead of a polynomial, we can literally approximate the data by using a basis function. So the basis function could be phi j of x, so that f of x will be the same as sigma j equal to 0 to the m a sub j phi j of x. So some of the common choices for the basis function includes the orthogonal polynomials like the Legendre, the Chebyshev, and the likes, okay? And then here you want to know that the technique works well for large data sets, you know, and this could be computationally expensive. So I wish we could look up an example, but I think I want to just run through some other details, okay? And then let's assume, for instance, we have g of x is the same as e to the x. And now this is taking over the interval 0, 1. And we have the basis functions, phi of x equal to 1. Another basis function given is phi of 1 of x equal to x. then another basis function is phi of 2 of x equal to x squared. So we know that here, the approximation function is the same as a0 plus a1x plus a2x squared. Okay, so here we want to determine all of these coefficients, and there the error function here will now be integral 0 to 1 g of x minus the function f of x all squared dx. So it means that we are not going to plug in this, and this will lead to the normal equations. And then once we do that, for k taking on values from 0, 1, 2, because we have 3 basis functions. So this will now look something like sigma j equal to 0 to 2 a sub j integral 0 to 1 j of x. This is more like having an orthogonal from the base, the inner product, right? X by k of x dx. So, but here we have 0 to 1, g of x is given, then times the basis function, right? The k. So we know k takes on values from 0, 1, 2. We have those 3 basis functions, okay? And afterwards, this is going to lead us to a matrix, which is G, Kj, to be AB by J of X by K of X dx. So this gram matrix can now be resolved. Once we solve that, then we can get the system of equations, okay? For what we have, okay? So they are pretty simple. If I have time, probably we'll try to work out some tutorials on that, but it's nothing complex at all, okay? And then one more thing I now want to mention. Let's quickly look up for the discrete, for the continuous. So we have the Legendre polynomial approximation. Now, the Legendre polynomial approximation is more like the Chebyshev polynomial, okay? Because these sequences form an orthogonal set defined over the interval -1, 1, okay? And the Legendre polynomial P of n of x satisfies the Legendre differential equation. Okay, and the Legendre differential equation is given as 1 minus x squared, then the second derivative of the Legendre polynomial of x minus 2x, the first derivative, plus n into bracket n plus 1, Pn of x equal to 0. And these polynomials are orthogonal with respect to the weight function. So in this case, we have a weight function to enforce orthogonality over the interval in this case, okay? And recall that for the Chebyshev function, we had 1 over square root of, 1 minus x squared. So in this case, we now have the inner product, -1 to 1, Pm of x, Pn of x, the x will be the same as 2 over 2n plus 1, Dirac delta Mn, where delta Mn is the Kronecker delta. Okay, so the Legendre polynomial can now be generated using the Rodriguez formula or the recurrence relation. So I'm going to put up the two. So if we use the Rodriguez formula, we see that Pn of x will be the same as 1 over 2n n factorial, the n, the xn, x squared minus 1n. But if we use the recurrence relation, we have n plus 1, Pn plus 1 of x will be equal to n plus 1 s Pn of x minus n Pn minus 1 of x. Okay. And from these two, we can equally put up the Legendre polynomials. So P naught of x is the same as 1. Then P1 of x is the same as x. P2 of x is the same as 1 over 2, 3 x squared minus 1. So we can go on and on, okay? P3 of x is the same as 1 over 2, 5x cubed minus 3x. Then P4 of x will be the same as 1 over 8, 35 x to the 4 minus 30 x squared plus 3. Now we try to follow the same system of analysis then to derive some few examples. So since you understand the Chebyshev technique, then this shouldn't be a problem. But don't worry, I'll find time to probably solve a few examples. Then we have the Laguerre polynomial approximation. So the Laguerre polynomial, say Ln of s, are a sequence of orthogonal polynomials defined over the range x, for which s takes on value of 0 to infinity with respect to some weighted function. And the weighted function in this case is the same as e to the minus x. So you know that this is quite different from the former, from the Chebyshev and the Legendre. And you know that the weight function ensures convergence of the integral over an infinite domain, because we are considering an infinite domain. So this exponential function will ensure convergence of the integral. And then this literally satisfies the Laguerre differential equation given as x, the second derivative of the Laguerre polynomial, plus 1 minus x, then the first derivative, x plus n ln x equal to 0. And we can also use the Rodriguez formula to generate the polynomial. So using the Rodriguez formula, we have that the Laguerre's polynomials are given as the Euler form of x over n factorial, the n, the xn, s to the n, epsilon minus x, okay? And also, we can literally put up some of the Laguerre's polynomials. L naught of x is the same as 1. Now, L1 of x is the same as 1 minus x. L2 of x is the same as 1 over 2, 2 minus 4x plus x squared, which will be 1 minus 2x plus x squared over 2. Then L3 of x will be 1 over 6 into bracket 6 minus 18x plus 9x squared minus x cubed, which will be 1 minus 3x plus 3x squared over 2 minus x cubed over 6. F4 of x will be 1 minus 4x plus 3x squared plus 2x cubed, 3 plus s to the 4 over 24. So we can literally go on, and then the general formula for the standard Laguerre formula will therefore become ln of x with the same as sigma, k taking all values from 0 to n, -1 to the k factorial. Then this is more like the binomial coefficient, which is more like the combination of n, k, s of k. And this combination, which could also be given as this, is given as n factorial over k factorial times n minus k factorial. So this forms the binomial coefficients, okay? And then the Laguerre polynomial literally satisfies orthogonality condition. Now that we have to move from 0 to infinity, Lm of x, Ln of x times the weight function, which ensures orthogonality within the infinite domain. The x will be the same as the Kronecker delta over n factorial, where delta mn is the Kronecker delta function. Okay. And if we also want to compute the coefficients, in this case, then an is the same as n factorial integral 0 to infinity, epsilon minus x, ln of x, epsilon minus x dx. Then an will be the same as n factorial integral 0 to infinity 2x, because we now have e minus x and minus x, then ln of x dx. So, and when we compute these integrals, then we can literally come up with some of the expression. Okay, so you can do this for, you know, for instance, when estimating this. So the Laguerre's polynomial are literally used for solving even Schrodinger equations for hydrogen-like atoms in quantum mechanics. So if you look up my notes on physical electronics, there we played with quantum mechanics and the like. So this approximation technique finds application there. You know, they are also used to approximate exponential decay functions, even in signal processing. Okay, so well, I think that is what we really want to cover as far as the approximation of function is concerned. But I made mention of something, so let's see if we could do this in 2 minutes. So like I mentioned earlier, it should be noted that norms measure the size or error of function of vectors or matrices, okay? And they also help in quantifying how well an approximation fits the actual function or delta. So norms are not used, cannot be used as some kind of approximation technique. They are not approximation techniques, okay? So the least square methods, or the least squares method, for instance, will minimize the Euclidean norm, okay, of the error vector to find the best approximation of the vector of the function. So if, for instance, we have a data set S sub I, Y sub j, or I, for instance, so here the least squares solution will minimize the error such that the norm of ax minus b squared will give us sigma I equal to 1 to n y sub I minus p of x sub I squared, which is the least squared error. So this literally actually is called the Euclidean norm. Okay, and we use 2 to designate this norm. Okay, so it ensures the total squared error is minimized. Okay, so you want to note that different function approximation methods use different norm to measure their errors. Like we talked about the Chebyshev norm, which is the maximum norm. Okay, so yeah, I already mentioned that. So even the splines use the Sobolev norm. Okay, Sobolev norm, spline. This is what spline uses. So we know that least squares approximation uses the Euclidean norm, and then this uses Sobolev, and then Chebyshev uses the maximum norm. Okay, so one thing I also wanted to pick here is that while norms themselves are not approximation techniques, They are fundamental tools in many approximation methods for measuring and minimizing errors. So then what is norm? If we say norm, so let us provide a formal definition for norm. So we can say norm. What is a norm? So we can say that a norm is a function that assigns a non-negative real number to a function or vector representing a size or magnitude. Okay, so that's what a norm is. And usually the function approximation, or as we've discussed so far, literally uses these norms to measure the error between an approximation function and the true function. And we designate the norm using the notation. Okay, and this must satisfy some properties. Okay, so I'll just take 2 minutes of your time, and then that will be it. So now we say that a norm of f must satisfy, one, that the norm of the function must be greater or equal to 0 for all vectors f in the space, and also the norm of f can only be 0 if and only if f is the same as 0, and we call this the non-negativity condition. And also the scalar multiplication of a function, the norm of the scalar multiplication of a function is the same as the scalar parameter, the magnitude of the scalar times the norm. Okay, so for any scalar, which is scalar multiplication. Then the norm also obeys the triangle inequality such that the sum of the sum of the norm of two functions is less than or equal to the norm of one of the functions plus the norm of the other function. And then I'll just mention the types of norms, and then that will be it. So in terms of talking about the types of norms in function approximation, we usually have the P norm as a generalization for norms, okay? So the most common norms in function approximation are the P norms, usually defined as P norm, the same as integral taken for A, the integral limits taking on values from A to B, mod f of x to the power of p dx, or square root p. Okay. So in this case, p is literally a positive real number, and f of s is the function being measured, and the domain of integration here is A to B. Okay. And you now know that the choice of P determines the specific norm used in the approximation. And now that we've described the general formulation for norms, we can now look up a few norms that we use. Absolute norm. Now, this is also called the Manhattan norm, okay? And we represent it as L sub 1 norm. So when you see this, so this is just the absolute. So we are literally taking the absolute value of the function over the interval. So we integrate the mod of the function, the x over the interval. And this applies if we are avoiding large deviation. So this measures the total absolute deviation. So when we are concerned with measuring the total absolute deviation, then we want to take the absolute norm or the Manhattan norm. And then we know this is robust against outliers because it does not square any error, okay? So it just takes the absolute values, okay? So they are literally used in robust regression models to minimize large deviations. And they're also applied in signal processing for noise-resistant filtering, okay? So at times you see some of those articles or publications, you just begin to see some of these norms and all of that. So they are literally trying to minimize errors in the system, okay? That's where norms come in. And then the major limitation is that it is computationally difficult to optimize due to non-differentiability at zero. And then the second type of norm is the Euclidean norm. So for the Euclidean norm, we use L sub 2 to designate the Euclidean norm. We also call it the least square norm. Okay, so the Euclidean norm of a function is given as the integral of the magnitude of the function squared, the x, all to the all in square root, right? So this applies when we are minimizing overall error. So we are looking at the entire error. We are not looking at the absolute error. So when we want to consider the overall error of a function, then overall error minimization, error minimization. So we apply the Euclidean norm. So it minimizes the sum of squared errors. So this is literally ensuring least squares approximation. So it is smooth and easy to compute due to the differentiability, okay? And then, well, we use them in least squares regression, polynomial approximation, and we also use this in machine learning for measuring the loss function. So when we want to measure the loss function in machine learning, yeah, we use the Euclidean norm. And one of the major limitations is that it is sensitive to large errors or outliers due to the squaring, right? So that's the advantage the absolute norm have over this. And then we have one more, which is the maximum norm. Or better still, we also call this the Chebyshev norm. And we use L sub infinity norm to represent this. And we actually apply this when we want to control worst case errors, okay? So it measures the worst case approximation error, okay, by minimizing the maximum deviation. And here we have the maximum norm to be given as the supremum of the magnitude of the function, okay? S taking on values from A to B. And we know that supremum is the lower value of the upper bound. Why, if we want to look at the highest value of the upper bound, then we talk about the infimum, right? So, so this is literally used in Chebyshev approximation to minimize the largest error rather than the total error. So you should take note that this is only targeting maximum error and not the total error. So the norm, it is the Euclidean norm that targets the total error. And so we use this in numerical analysis for uniform convergence. And it's also applied where worst case errors must be minimized. And okay, what's the limitation of the maximum norm? Well, it does not account for the overall error behavior, like I mentioned, which Euclidean norm does. So this only takes care of maximum deviation. Then the final one I'll mention just before we say goodbye for today is the Sobolev norm. Okay, so this literally applies when we want to ensure smoothness. Okay, so the Sobolev norm, Kp, is given as sigma for I taking on values from 0 to k, and then this takes f of I e to the p1. So here, the Sobolev norm is used in spline approximations and finite element methods. So it takes into account both the values and the derivatives. So this ensures smoothness. And it is applied in partial differential equations, which we are going to talk about later. And it's also used in image processing for smooth approximations, although it is computationally expensive. So, well, I would have also looked up a few examples. I think we'll see if we'll be able to reserve that for tutorial session much later. So I think this is a good place to stop for now. So do we have any question? Someone just said something.
Yes. Before I proceed, I have to tap into that time.
Well, I can hardly hear you.
Yeah. Okay.
So much for today's lecture.
Okay. Yeah, too much really.
Yeah. Please, but before I proceed, please, I have to plead on behalf of the class. Please, if exam remains 3 weeks, please have to give us time for rehearsing and go through what we have taught us. Please.
It's fine. It's fine. It's fine. It's fine. So we'll walk with your pace. So we discuss an appropriate time for exam later then. So let's say when we're done with lectures, then we'll discuss when we'll be ready for exam.
All right.
Okay, sir.
Thank you.
Doctor, sir.
Okay. Go ahead.
Yeah, we are going to do some tutorials regarding all these calculations that we are yet to touch, right?
Yeah, I'll find time I'll see if I'll be able to work out a few things, then upload, just like I did in others.
Okay, sir.
Yeah. Okay, I think it's time to say okay,
sir,
go ahead.
a question.
Go ahead, please.
Yeah.
Please, good afternoon. I don't know, sir, if you can actually have a relevant material to actually consult with respect to the course.
Okay. Yeah, I think I sent the teaching plan and recommended some textbooks, right?
Yes.
Yeah, so probably you want to look them up. I understand most textbooks may not show all the details. That's why I try as much as I can to show all the details. We just want to make things as simple as it can be in class. So when you look up the textbooks, they don't look too foreign. Okay.
Okay.
Yeah.
Thank you so much, sir. Thank you, sir.
Subscribe to his YouTube. You'll see everything.
Yeah, and you can also look up lecture notes. I'll try as much as I can to upload these notes to the YouTube channel. So you also want to look up what we have there. It should be helpful in terms of revising over and over again. So I think for now, I want to say...
Just a question, sir.
Okay.
Sorry.
Go ahead.
Yeah. Looking at all of these norms, we find out that they have limitations and they have advantages.
Mm-hmm.
So are there case scenarios where we can combine two norms together because of the advantage it has to solve a problem?
Yeah, it depends on the problem you want to solve. So we want to figure out such a case study first and then see how it applies. But we use norms in our engineering discipline to simplify our mathematical analysis, okay? And you could literally move from norms to Banach spaces, to Hilbert spaces, depending on the vector space you want to perform your analysis in. But as far as approximation of function is concerned, what we are bothered about is how we could minimize the error in the approximation of the functions. Because we want to use functions that will match the actual data. Okay, that's our goal. So we want to ensure that the convergence is smooth and it is not computationally intensive or expensive, and that the error margin between the actual data and the model we now use to represent that data matches that data. I don't know if you get what I mean. So let's assume you go for feed measurements. Probably you go to NIMET and you take your wind data. That's what you want to use for your research. So now you want to analyze the data so you're able to come up with a particular feedback to say, well, we can implement some form of renewable energy in this region, probably using wind energy and all of that. Now you have raw data. Now the raw data does not make sense to us. Now, if we have to now come up with a renewable energy plant, now you should be able to represent what you have with a mathematical model that will be able to develop. Because we already know once we have the mathematical model, we should be able to synthesize the system. So I know most of you already played with that. Okay, so if for instance we have an integrator in the system or a differentiator in the system, what do we use to represent that? Okay, so you can begin to tell whether I want to use a capacitor or an inductor when we are trying to now come back to circuit element model, and then you want to develop controllers for a system. So from the mathematical model, we are able to now pull off the system, or better still, the electrical component that will be able to interpret or represent that particular equation you just put up there. So the idea is we want to represent the physical phenomenon with some mathematical basis that we can translate to design. That's our goal. Okay, so now you now have to come up with an approximation of that data. To say, well, we can't just put all of this data that runs into hundreds of pages into a model. So you want to say, well, this equation represents this data. So it means you are literally performing approximation of function for that data. So you have come up with a model. And for those of you that are really interested in all of those degrees, you say, well, I generated a model for wind and I published it and this is it. But beyond that, we want to use that to develop something. So the question you now want to ask is, does that model truly represent that data? So because it's an approximation of that data. So it means that the error margin between the actual data and your generated model must be very small. It should be as close as possible to zero. Okay, so we are now saying, how do we estimate that margin? We can use norms. And we just mentioned that depending on the method you are using for approximation, that will determine the particular norm you will use to evaluate the difference or the error margin between the actual data and your generated model, or which is the approximation of the function. I don't know if that makes sense.
Yes, it does. Thanks.
Yeah. So if you are not using least squares to do this approximation, because most of the time I want to use least squares because it's very easy and straightforward. So you know that if you want to evaluate the error margin, you are literally going to be using the Euclidean norm. You can't be using the Sobolev norm to check for the error difference between your actual data and your least squares, because that is for splines. Do you get what I mean? So what we just did here is to say, well, these mathematical tools can be used to solve your problem in terms of telling the error margin between the actual data and the approximation. Is that okay?
Yes.
Okay.
It's okay. Thank you.
Okay. So I think for now we can say do have a great day. Hope to see you in our next class.
Thank you, Doc.
Thank you, sir.
Thank you very much.
All right, thank you so
Thank
much.
you, sir.
Bye-bye.
Thank you.
Thank you.
Okay.
Thank you, sir.